Right. So it's a pleasure to get to start off these Geo-PIT talks this morning as we look into the future and we think about what that means for us as geotechnical engineers. I'm going to spend the next 12 minutes talking a little bit about some of the technologies that we've used in my group at the University of Arkansas and how we see those moving forward in the future. And then I'm going to also challenge you to kind of set aside your practical engineering hat for a minute and allow yourself to dream with me. 3D printing or additive manufacturing. So my talk was entitled Emerging Technologies. I'm going to stick to these two today, really in the same thing. So if I talk about additive manufacturing, there's essentially 10 main processes that are available today. These are the 5 kind of main types, and the others are really just sort of variations from these. The 2 that are most interesting, at least in my opinion, as geotechnical engineers, are the bottom 2 listed here. So we have powder bed binder jetting on the left, and then an extrusion type device. So the powder bed binder jetting essentially is powder spread across, and then an inkjet printer cartridge, same as you would print a piece of paper or ink on a piece of paper, moves across and actually spits out a binding solution wherever you want that 3D part solidified. And then the extrusion, there's several different types of technologies and materials, but I'm going to sum that up just by calling them extrusion. It's essentially just a paste that is extruded through a nozzle into its 3D form, and then it solidifies there. Now, most of the 3D printing, and I have to give credit in the audience to Ryan Beamer. He was a colleague of mine, a friend at graduate school. Cassie and I were, duct taping everything together to get it to work, and Ryan was essentially 3D printing these beautiful things and had this wonderful looking lab. And so that's where it all began for me. That's what got me thinking about how can we use 3D printing, additive manufacturing in our laboratories. Not only for laboratory fixtures, so we've done things like printing the shear plates for direct shear devices. We've printed, holders for sensors, things like that. But we've also taken it a step further, and we've looked at it as a way to study fundamental soil behavior. And so one example I'll give you this morning is if we look at sands, we know that as angularity increases, the strength of these sands also increases. And there's a lot of us in the audience and a lot of us here at this conference that are interested in trying to peel back that fundamental relationship. When we look at natural sands, if I were to grab a bunch of these and go test them in my lab, one of the difficulties I have is that natural sands vary in mineralogy, surface properties, shape, obviously, and then also gradation. And so it really is a challenge to single out the contribution of that strength just from shape alone. And so one of the ways we approach that in my group is to create what I call analog soils. And these are essentially 3D printed replicas of these natural soils. We can do anything from a sphere like you see here on the top. Oh, wrong way. Right there, those are 3D printed spheres out of a gypsum kind of composite material. And then we have the exact same material and process we've used to 3D print an Ottawa sand that has been scaled up. So same gradation, same material, same surface properties, and we're able to actually single out the contribution from shape alone. And we set it up in some sort of large-scale triaxial or direct shear, direct simple shear test, and you can see we derive these sort of stress-strain relationships, volumetric behaviors, and we can really start to examine those. Now that's great for us. On a larger scale, a lot of the work that has been conducted has looked at applying these technologies to construction. And so we see these in larger formats, different types of systems. Here you see an example of an extrusion device. I've got a video that hopefully will give you some indication as how this is actually working at that scale. I have to give credit to the group at the University of Southern California, but also this startup company that was created called Contour Crafting. I'm stealing their video because it's better than any of mine. But basically, they are able to create 3D objects. This is an example where they're using kaolin clay. So this would be similar to kind of a pottery clay. We could make structural elements, things like that. They're showing it on kind of a smaller scale here. But then in a little bit, they'll show that this can be expanded to larger scales. And so the same company has created a way to do this with concrete. And this is a lot of what we're seeing in the structural world these days. They're looking at concrete buildings. The Army Corps of Engineers actually has printed concrete army barracks. And you can do anything from a wall section all the way to large buildings. And so I would encourage you to go out and look on the internet. There's all kinds of institutions now that have these 3D printers, and they're doing this at really large scales. And a lot of the focus has been on trying to create or sort of mass produce structures. Now, when I think about the advantages of 3D printing, one of the things that I'm interested in is looking at a little bit beyond that. So not to discount any of that, because I think it's amazing what they're doing. But there are some advantages where when I look at a printer like this is one out of Catalonia, in Barcelona, basically, and it prints soil as well. So it's also an extrusion device. And they're wanting to print houses. And so I think in the future, if I'm looking at this is pretty neat. Basically, in locations, if you're thinking about places in the world where we don't have aggregate, we don't have cement, or it's difficult, to try to bring other materials in, why not use the soil that's on site? And that's been our kind of push in my group, and obviously here in some other groups as well. Now, the interesting thing for us as we take this a little bit further, and maybe this is because I kind of exist in a research side, this is really where I want you to sort of think and take off that engineering or the practical side of that hat for a little bit and dream with me. In my opinion, where this is going to be really impactful for us is thinking about shapes that we can't create otherwise. So when you think about construction and you think about the infrastructure that we create, in the majority of the cases, we're trying to be somewhat efficient in terms of being able to produce it and make the construction process as easy as possible. Most of that is due to the fact that there are low margins. So when we're looking at this from a practicality side for construction companies, it's going to be hard to convince them to implement some of these things unless we can get it to where maybe it can't be constructed otherwise, or we can get these margins fixed. And so I think the real goal and the real application here is if we think about shapes that we couldn't otherwise normally construct now, this is where 3D printing is going to be important for us. And so these are some examples of things that we're working on in my group. You can see on the left just some examples from nature. These are materials or geometric patterns, basically, that end up giving a really high strength-to-weight ratio compared to the actual constituent materials themselves. And we have looked at honeycombs and other things like that. Let me go back for just a sec, if I can. There we go. This is I keep hitting the wrong button. There we go. Mercedes-Benz has come up with a bionic car, and they're basically looking at 3D printing as a way to prototype, but also as a way to actually construct these things. And it goes way beyond the conditional or the typical construction practices nowadays. Now, I'm stealing this again from Jason and others in the room, but if you look at the picture on the left, there's quite a few researchers interested in looking at this biomimicry or bio-inspired design. Their group has looked at tree roots and basically said, so that if the Center for Biomediated and Bio-Inspired Geotechnics, I'll give them the credit here, obviously, but they've basically come up with a schematic to try to show, tree roots as anchor systems, foundation systems, to really understand how those systems work. Now, in the past, if we think about the way that we construct foundations, piles, or we think about anchor systems or soil nails, it makes it difficult to imagine how we could construct these otherwise. And so recently at Stanford, a group has come up with what they're calling kind of vine bots, and they're essentially soft robots that allow themselves to grow. They can get into tight crevices, as you can see here, and they can actually expand. And so imagine putting a print head or a nozzle, extrusion nozzle, at the front of this type of vine bot. And now you start to picture, okay, if we decide that tree roots maybe are the future and that's what our system should look like, now we're starting to get ways of actually constructing that. These are what I like to call tuned or macro fabrics. And I don't know that that's the best term, but that's what we're going with so far. Again, the honeycomb pattern is one that's pretty simple for us to use as an example, so I've shown that here. We've looked at it both empty and filled, and what we find is that there's really high strength-to-weight ratios compared to just a normal sort of layering or compaction technique that we might use currently. And so a really kind of, crude schematic that I put together is just to look at this as think about, again, places where we don't have aggregates. We can't bring in pavements. There's not concrete that's readily accessible. And so one option is to actually create this. If you want to think of it, those of you familiar with geosynthetics, maybe it's like a geocell without actually having the geosynthetic there. You're essentially using that binder jetting process, and you're solidifying it into these patterns. And so you're able to carry more load. You have better performance. And we're essentially letting the soil do more of the work for us. The figure on the right is an example of a negative Poisson's material. The pattern itself is actually what's creating this negative Poisson. So something a little bit different than we're normally thinking about when we think about civil engineering materials. If I load this in compression, the interesting thing is the walls actually contract or squeeze in. So that's different than our normal materials, and there's quite a few applications, at least, that we're envisioning that this could be very useful when we think about fills. So again, the only way to construct that would be this kind of 3D printing application. Now, I've just kind of said this or added this for fun. These are 2 videos, again, back from this contour crafting. My friends thought I was crazy when I started talking about doing this on the moon. Stacy's shaking her head. But there really is a lot of talk in NASA right now, a lot of talk in the European space agencies, and they're basically looking at ways of either creating landing pads on the moon or Mars, or actually creating habitats. And so I want to just leave you with this. Allow yourself to dream. Allow yourself to think about, if we didn't have to have rectangular cross-sections or circular cross-sections, is there a shape that makes more sense? Is there a shape that performs better? Is there a way to do this and not let yourself get limited by the current construction practices, but let yourself think about how to do this on Earth, but as well as beyond. And you can see here they've got an extrusion technique as well as more of a powder bed process. And this is one of the only powder bed processes, I should also add, that works in a zero gravity environment, which is pretty cool. So a different type of challenges there as we look beyond Earth. But with that, I will pass it on to the next speaker.